this is the title of Machine Learning for Self-Driving Cars, and the subtitle here will be Behavioral Cloning, because we can't cover everything in this domain in half an hour talk or an hour talk. And behavioral cloning is basically the concept of mimicking the behavior of human drivers. So not really aiming towards necessarily an optimal driving, but we just copy humans with a computer. So just a quick background for myself and why I am the one standing here. I do this in my day job. So I work with renewable energy, small scale. So mostly wind and also solar, batteries. We install that on islands and mountain tops and wherever there's a lack of grid alternatives. But prior to that, I did some software development for Volvo construction equipment. You can see some examples here. And it's basically really building on these experiences that have come to this field of self-driving cars. Okay. So just today we're going to go through self-driving cars in general a little bit, and then behavioral cloning, what that is as an approach, and also which tools that you would use. In this case, for example, neural networks. And then a little bit the pipeline of how do we collect the data, how do we use the data with the tools that we chose, and we'll also have a demo or two at the end to show what it really looks like when we do this development on a prototype stage. So the context we have here is half a year ago, I enrolled in a course called Self-Driving Car Engineer Nano Degree. So you see here. It's made by Udacity, which is an online learning platform founded by Sebastian Thrun, who is probably the #1 legend when it comes to self-driving cars. He founded the Google self-driving car team. He won the DARPA challenge in 2005 with the first self-driving car that drove hundreds of miles through the desert. So if you have to pick one person who is the #1 legend, it's Sebastian Thrun. He also founded this company, and this is sort of his brainchild as well. So I enrolled in this program, and actually today what I'm presenting is one of the project submissions that you are required to do when you go through this program. Specifically, this project was sort of inspired by a paper, a small paper. It's 7 pages like this, written by some engineers at NVIDIA. And for those of you who have played computer games, NVIDIA is the manufacturer of these cards that you put in your PC to run really intense games with heavy graphics. But they also do hardware for self-driving cars, really like high-power stuff. So what they did in this paper was that they equipped a car like this with a front-facing camera here, taking pictures of the road ahead, and then a human driver driving around for tens of hours, and then they record the photo that the car takes of the road and the steering angle of the driver, and you use that to teach the car how to drive. So just to clear things up a little bit, because we have all these names, right? This is also borrowed from NVIDIA, good friends at NVIDIA. We would call artificial intelligence everything that spans back from, you see, a really long time ago. And in the broad sense of artificial intelligence, we say something where a computer makes a cognitive decision, sort of, that is not that pre-programmed. You could also say that artificial intelligence, and especially general intelligence, is what comes all the way at the end, where a machine can do everything. So the terminology is a little bit confusing, but this is what a lot of people will refer to. Machine learning comes a little bit later. It's more of a tool within artificial intelligence to achieve this. So you see this spans out, and this is sort of a subset, okay, included in here. And this example is good. This is where you could read postcodes with a machine on letters used by the US Postal Service really early on, right, instead of a human reading. When we come to this is deep learning neural networks, and this takes it one step further. The theory of deep learning dates back decades, but it was impossible to do until just very recently because there was no data and there was no computing power at that scale. So when you hear these terms, they sometimes mean a little bit different thing depending on who says it, but this is a pretty broad understanding of what we do mean normally. And this is what we're going to look at today, right? Specifically on this one, a small part of it. So let's zoom out a little bit and just talk about what we're going to go through today. So these are the components. And we're going to look at self-driving cars, specifically behavioral cloning, and as an approach, and then these two, machine learning and neural networks as tools. And to zoom out a little bit, why do we do this? Why is it worthwhile? So since you're here, I think you're all interested in self-driving technology. Most of you are probably seeing it as a good thing on balance. There are many things to be critical about as well. But there certainly are some really, really strong advantages. So one is, for example, space in cities. We use, in many big cities, more than 30% of the land is for streets and parking. Very valuable land, very, very wasteful, right? Cost, obviously, if we can have trucking and taxis without paying a human driver, then we reduce cost, we increase productivity. Accessibility, if you are too young or too old to drive, or you can't see well, then if you have good public transport, you might be okay. But in many parts of the world, that's not the case. You need something else. I would also argue something that's maybe not viewed as that obvious, but there's an environmental aspect to it as well. Because today we have cars standing parked about 95% of the time. Is normally the figure that we get taught. So 5% of the time it's actually driving. Okay, that can easily be increased by a factor 4 or 5, maybe even more. What does that mean? Well, at the same time, we have an electrification process. But today, electrical vehicles are expensive to buy, very cheap to drive. So the more you drive them, the cheaper they get in comparison. Self-driving cars running maybe 5 or 6 times as much will quickly eat up the extra cost in the beginning. And when these are on the road, you could argue maybe it's in 3 years, maybe it's in 5, maybe it's further down the line. But at that time, that battery cost is much lower, so it will be extremely expensive to drive these cars on petrol or diesel. So that's it. That's game over for petrol. Unless you want to do it for fun. Just like today, we go riding horses, we go sailing boats, but it's not for transport, it's for leisure. Right? So that's the background on self-driving cars, why that's a good idea. And there are more reasons, but that's what I find most compelling. Behavioral cloning is sort of a fun way to look at the problem instead of writing specific programming rules. And you can feel the intuition behind this in a way that if you put a kid next to a driver, that kid will, without instructions, without reading, without being explicitly told, that kid will soon understand when the driver stops for a red light or a stop sign or keeps within the lane lines of a street. It's something that you can copy quite easily. So with the tools we have in machine learning and neural networks, we think we can do that with computers as well. And then machine learning, neural networks, that's just the way to do it. We just feed it loads of data. We be smart. Here we have to be quite smart in how we choose the features, what to look for. When we go to the neural networks, that's no longer the case. Then we can learn what to look for, or the computer does it itself. And maybe really the most important thing thing when it comes to self-driving cars is safety. So we do believe generally that self-driving cars will be much safer than human drivers. And just to give the scale of the problem we have today with safety on our roads, we have about 1.25 million deaths a year and many more injuries. And just to give a visualization of that, this is how many people die in plane crashes every year. About 250, 500, sometimes 900, depending on if there's a big crash. And this is 1.25. Right, so flight safety is really important, but this is how important road safety is. Factor 5,000, roughly. So it's a problem that's worthwhile solving. Yeah? Okay. A self-driving car, this is Waymo. This used to be the Google self-driving car. The one I showed right at the beginning was a Stanford car that is the successor of the winner of the DARPA challenge. This is the Google car, one of the Google cars. They spun out that initiative as a separate company called Waymo. And you see some cool sensors and stuff on it. A self-driving car, very simplified, is a three-step process. So we begin with perception. We have all the sensors that find the environment. We have lasers, cameras, radar, sonar, or ultrasound. And then that feeds into an analysis. This is the deep learning part. And we make a decision what to do. And then we do it. So this is basically the wheels turning, or it's acceleration, braking. And this is robotics, right? Really important, but we're not going to talk about that today. So we are going to gray out most things. We're going to keep the camera, which is part of the perception, and then the analysis. So that's what we're going to zoom in on today. The fleet part that I put here is really related to safety. So today when there's a crash in India or Japan or Paraguay, I learn nothing from that. There's no experience that I can benefit from. Even if there's a crash in Malmö, I'm not going to learn from that experience and become a better driver. When we have connected cars in a big fleet, we can upload that crash data from every single car that was involved and connected. And then every single car that is connected then and every single car that's going to be manufactured in the future will learn from that experience. So by the time we release the cars and we collect data, it might be roughly the same as human drivers, but it's quickly going to overtake. And then it's going to be severe risk to drive it manually in comparison. Right, so let's look at behavioral cloning. And intuitively, the same thing here. If you drive a car, we looked at before on the previous slide, loads of different sensors measuring in different ways, right? But a human, when you think about it, doesn't use LiDAR, doesn't use radar. We use our eyes. You could argue maybe you listen to traffic a little bit, but if you covered your ears, performance wouldn't really change. Even if you covered one eye, you could still drive pretty well. So you don't even need stereoscopic vision. You need one camera, one eye, and then your brain. So that's what we want to mimic. We have one camera, and then one neural network. That's sort of that's our approach to it. It should work intuitively, because that's really all the data that we use when we drive manually. So what we're going to do here, we're going to make a simulation of the NVIDIA project. So they were driving up on the east coast of the US, and we're going to drive in a simulator. So this is the hood of the car. So we're going to drive around in the simulator. It's basically a computer game. We take photos in front of the car, like this, and then we record the steering angle of the car. So straight ahead would be 0. All the way to the right would be +1. All the way to the left would be -1. So that's what you see here. Here's a curve to the right. Okay, it's +20. Here's a curve to the left. It's -30. So I'll just show you how we do that in practice. Let's see here. Demo. Okay. So we fire up the simulator that looks like this to begin with. This was built by the team at Udacity, but it's now open source. So you can search for Udacity simulator self-driving car, and you can actually modify this simulator as you wish. That's pretty cool. All right, so let's just play here. I'm going to do with quite poor graphics because otherwise my computer can't handle it. All right. So you see it's from Udacity. We'll do now training mode, which is where we collect data. Okay. Let's see. Maybe we'll do it windowed so we can see the entire thing. So if I now drive manually with the keyboard, you can see that we are going around the track. Sometimes we go to the right, and we need to make sure that we are checking quite a few different options. We might want to also have some recovery data, so we're maybe very far to the right and then going back in, and the opposite. Right now I'm not recording data, but basically if I were, you would see up to the top left you have numbers going negative when I go left, positive when I go right. And those are going to create data pairs of that number plus the picture of the camera that's facing the road in front from the car. Okay, so that's what the data collection would look like. Really simple. Okay. Yeah, I'm not actually doing that. So in the model when we drive later on, we're just going to set a throttle like this is it. But you would do that. What I did actually was I set a speed and sort of a control that I want to maintain a certain speed. But absolutely, you would, if you were in a more complicated environment, maybe if you're going downhill and then really sharp turn, you would want to correct for that as well. Okay. So now here's where we run into the first problem, because when we look out of the car, we will see red lights, stop signs, lane lines, and things in the roads, signals to us that were designed by humans for humans, that are easy to detect. Right? We do that by colors, for example, white lines or red signs. But all the computer sees is this. So this is quite tiny text, but here's each pixel of this image, and it's just an intensity going from 0 to 255. And if there were lane lines in here, like maybe there are, but it's, for us it's difficult to see. For a computer, it's difficult to see as well. So somehow we have to transform this into some knowledge, some insight that can give us a number between -1 and +1. And that's the job of the neural network. Right? And you can imagine, how would you code this by hand? It's really impossible. And that's why we need the neural network. What you could do is something like this. So we take, here's a road. These two in the top row belong together, and these two do. So what you could do is to say, okay, what's important here is this line and this line, if we're going to stay in our lane here. So then what we do is we sort through the intensities. And intensity is basically brightness. Okay? So this part is really bright compared to the asphalt. So is this. So if we set a limit somewhere, or maybe even we set a contrast limit, how much it changes from one pixel to the next, we will get maybe something like this. And then we will have to filter out all this noise and maybe make sure that, these are very short lines. So maybe we discard them. We need them to be 40 pixels long before it's actually a real line. But then maybe something is torn off here, right? So maybe we want to extend it here, and you start to create all these exceptions. And you can imagine this is just a California road. Then you have to take account all the different places you're in, and loads of statements, if then, to account for all the situations you can end up in. Similarly here, this is a straight road. That's quite easy. When you have a curved road, it gets a little bit trickier. But still, you can kind of make an analysis to say, when there's a sudden change in brightness, that's probably a lane line. But you can see maybe here we have shadows coming in. That's a sudden change in brightness. So now we detect that here as well. And that's wrong, right? And that means that it's okay, we have an algorithm that sort of only takes part of it that's along the track, but it's still going to be pushed one way or the other. It will get you started, but as the problem grows and as your scope grows, it just becomes impossible to keep track of. It's not a scalable solution, really. So, but if we had, let's say, if you with this want to, what you could get if you had a proper location here is basically what's the distance to the right of the lane line, what's the distance to the left. Also, once you have this, now with this line that we have fit, or this curve, we have the curvature of the road. That means we know how to steer. So if we do get these properties, these features, we have enough to tell us what to do. So that's a good part, and we could use quite simple machine learning to take this insight into steering wheel command. That's quite easy, right? But again, the problem is how do we get to this in a robust, reliable way based on just the pixel input data? Right, so we do that with neural networks. And we call these, this is a diagram of the artificial neural network in the computer. And this is well, not a picture of it, but sort of a drawing of it in the human brain. So you can see why we call them neural networks. And basically what it is, you have all these small neurons with dendrites taking input information. If there's a biologist here, like, correct me. But we have input information to all the neurons, and then output synapses as well. So the neuron is flicked on and off, and it sends out small jolts of electricity to send the signals forward. And this is really what we're trying to mimic. And the beauty of this, or the power of this, is that, so let's draw a little bit here. If you had some inputs here, so we could have an input number saying this is the distance to the edge of the road to the right, this is the distance to the edge of the road to the left, this is the curvature of the road ahead. You took those numbers and you multiplied them with a number, just a random number to start with. You get an output, and you know what the output should be because you recorded that data. So you change your coefficients here. These are normally called W for weight. So let's say 1, 2, 3, 4. This is as technical we're going to get today, right? And you can make this multiplication. It's probably going to be a little bit wrong. So you change the weights again, and you keep on trying until you get close to the truth. But this relies on the input being high quality features that are really useful. So if you just plug the pixels in here, it's not going to do anything for you. if you plug in the real insights of your position, it's going to be great, and you're going to get your steering angle. So what we really want to do, we want to increase the complexity and sophistication. And with a neural network, what we can do is that we take this sort of linear regression machine learning, which is the simplest form of just adding linearly these inputs. And we do this. So we start here with the pixels. And then we have a second layer which takes the input of the previous layer and so on. So what we will find here is here's just intensity, pixel intensities. But in the next level, we're combining the pixel intensities to find something a tiny bit more sophisticated. This could be a line or just a contrast. And as we go along, we can actually add another one. This is another layer. And if this were, we usually do this for image recognition. Like if we are now looking for cats in videos or other important problems, then this can be an edge. This could be a shape, like let's say a triangle. That's an ear maybe, or maybe it's or we can finally find some kind of texture in the fur, and sort of heuristically. We normally, like a lot of times, we don't really know what happens in these layers. We have an intuitive feel, but we don't normally really know. But it doesn't matter. As long as it works, it's okay. And the more layers you have here, as this expands, the more sophisticated it gets, and the more complex data it can represent. But it also needs more data to work. So basically, we've gone from here. This is machine learning, as you know it, quite classic stuff by now. And instead of having this as the input layer, we have the input layer over here. This is the output layer of the input layer, which becomes the input layer of the next layer. And all these layers now that are not the initial input layer nor the output layer, these are hidden layers. And the size here is basically the depth of the neural network. So as you start adding up, this is deep learning. That's it. That's the magic word that people throw around. And it's not any simpler or more complicated than this. And then this causes problems a little bit. What's nice with this traditional one is that if we have the inputs here, now we can look at these weights or these coefficients and find out if it's important or not, because we just look at this. If this is always 0, then we know that regardless of what we put here, it doesn't have an effect. So we know that this feature is completely useless. It's very difficult to do here because it becomes really complex, and this particular node might not really mean anything. But as it contributes in the layers coming forward, it actually does have an effect. So this causes some trouble in debugging and developing. So you basically have to sort of try your way forward and see what works, what doesn't. And sometimes it's just really surprising and counterintuitive even. Yes?
Do you program for example, the stuff that takes lines, or do you make it learn that part?
So what you do, and one of the important jobs, is to decide, okay, these inputs are going to be the pixel inputs. So if we have a 50 by 50 image, that's 2500, and then maybe you have different colors as well. So that one is quite fixed. But then you as an engineer have to decide how many layers are we going to have, and how big are they going to be. It's not common that they're all the same and that they're all the same as the input. So that's part of your research to find the optimal solution. And these layers, as I draw them here, they are fully connected. So each neuron connects to then all of the neurons in the next level. And that's good for complexity. You can really represent very complex things. But it requires a lot of resources, and it's prone to overfitting as well. So there are ways. The problem with this, if we just stack them up like so and then put another layer, is that if we go back to the slide here, the problem with that is you're just taking all the pixels, putting them into the next layer, and they connect to the next layer, which means that this one, for example, has the same relation to this one as it does to this one, because they're all connected. But obviously in a photo, that's not true, because these here are very strongly correlated, and they mean something together, whereas this and this don't. So, and the way we can account for this is convolutional neural networks, and using convolutions and reusing weights. But that will be for part 2, because it will be a little bit too long to do today. Yep.
So would you say that more layered or more prone to overfitting?
Yeah. So the bigger it gets, the deeper it gets, and let's say the wider it gets, the more information can be stored in the weights. So we get basically these weights we have here. We have one for each here as well. So if you don't have enough data, these weights will basically remember all the data points that you had. So, and because it's so powerful, once you throw the same data at it, it will perfectly 100% give you back the answer, but it will not generalize. So if you give them a new situation, it will not be able to draw general rules. And that's basically why we can do this today, because just a few years ago, we didn't have, for example, tens of thousands of or millions of images that were tagged with the content, right? Like you would have today on Facebook or Instagram or in other data sets. So that's really the huge leap forward we were able to take, because we knew what those images contain, and we can then train and evaluate those neural networks. The next step is going to be, like we take this a little bit naively and throw it into a demo, see if it would work, just using this approach. How are we on pizza time, Diana?
We have like 12 minutes.
Okay, good. So we can do. Yeah. Are there more questions? Yeah.
Are we talking about overfitting, like they're more, like what does it mean overfit?
Yeah. So we can maybe. I have a slide on that, but we'll take it between the demos. So if we just take the data that we that have pre-collected and then run it through a model without really tweaking anything. Let's see. And we'll see if it works to drive. So we do. So I want to run this here so that it's a small screen. Okay. So now we go into autonomous mode. So here now you can see to the left is the steering angle that it gets. To the right is the throttle. And I've set it to a fixed speed. So now it works in the beginning quite well, because it has learned to stay sort of within the lanes. But obviously it's a bit of a safety hazard at this point, so we wouldn't release this quite yet.
How much training data was that?
Yeah. Yeah. Oh, yeah. So that's basically. So what I've done here is I haven't properly pre-processed the data and not trained it for very long. So that's why it's not behaving properly.
So was this behavior based on the initial trip you took 10 minutes ago, or?
No, that was actually more data. It was that was 8,000 samples. So and it takes, when it records, it's 10 hertz, so it's 800 seconds, so 12, 14 minutes of driving, but not enough training. So what we do when we train is we have a photo and we know that it should have a specific output. Let's say it should be plus 0.3. So we feed in all the pixels, and then we have some initialized weights here. We multiply and then we get some new values here, and then we multiply with the second coefficients, and we go all the way. We get the number, and maybe it's minus 0.2, so it's very far off. It's really bad. So then what we do is then we change these weights a little bit all the way through here in the way that we are told by some maths called gradient descent or another algorithm. But we propagate these changes all the way back, and then we throw in a new photo with these new weights. And then we calculate all the way to the end, and then we get probably not spot on the right answer, but we get some clues in which way to go, in which direction. And then we update all the way. And we do this through all of our data, and then we start again, and then we start again, and we just keep on going thousands or millions of times. And this is why you need big computers to do this. And then at the end, it may work well or not. So that will maybe inform you how to change the architecture, the shape of this. And then you try again. Yes?
I'm going to ask Armin about why we are going to use cloning behavior for driving. So in this case, you are cloning the human behavior, and you are already terrible at driving.
Yeah. No, it's basically what we're cloning is something called end-to-end. So it's just seeing if the computer, based on just the photo, can actually make the right turning decisions. So we would want them to feed it. We train with data, we collect data, but we'll only give it data that is correct, right? So if you went off the road, you wouldn't teach it with that data.
How do you judge what's correct and what's not correct?
In this case, so you drive around, like the NVIDIA engineers, they drive around for hours and hours and hours, and then they download the data. If they know that something went really wrong, you don't want to use that for the training.
I'm going
Yeah.
to say, like, for example, like if I'm in traffic light,
Yeah.
if I'm human, I still have this slow reaction about seeing the light and then move. And if I'm driving, like, I have to keep really long distance, safe distance, because I also have slow reaction. But my ambition to have like self-drive car, that I will be over my ability as a human.
Yeah.
So if I clone my behavior as a human, then I didn't get anything advanced more than me.
Yeah, yeah. No, I see what you mean, and absolutely, that's what you want to aim for. So, and if you strictly clone, then obviously you wouldn't get any better. But it's more of an example of approaches that work. For this situation where you want to be quicker, obviously, if you have connected cars or robot cars all in line, you could drive with almost no distance. But in this case, it's more, rather than copying the entire behavior, the human behavior, it's making these connections between what does the camera see and what is the steering output.
The other thing you mentioned at the beginning that the input that we have as a human is our eyes.
Yeah.
But in actually driving, actually we have more mind than the eye, the sensor. We have our ear, we have our feeling of if the road is slippery or not, and far more other things that
You have that, but I would argue that, you know, if you were not allowed to listen, I think when I listen in traffic, it's mostly, you know, if you hear a police car or if someone's honking the horn, but that happens, but it's very small minority. So this is more, so yeah, let's put it frankly, this is more of a proof of concept of what the neural network can do based on this very limited input data that you would find difficult to map normally to, or write for sure an algorithm deterministically and say, based on these pixels, what should we do? Extremely hard to program unless you have a neural network to do it for you. Yes?
Yes. Wouldn't you want to train it on recovering from bad situations as well?
Absolutely. Yeah, it's really important.
Do that to not get the bad data that started that situation.
Yeah, so what I think you mean is,
Like when it went off the road.
yeah. So if we have a road like this, you want to have some data points where the car is here and with the wheels trying to center back, right? But you don't want to train to get there. You don't want to have your car here and collect that data going to the right. So specifically in the simulator, you know, you had let's see, what I would do manually in this case is there is a toggle, a keyboard shortcut to press record here when I record it. So then I'll probably go out here and then start steering back and then hit record because basically what you want, as you identified perfectly, is I want a lot of examples that are out here but with the steering wheel going back. Because if all I do is train driving in the middle of the road and just keep on going straight, then it doesn't know what to do when it's off. And you're quite correct. I don't want to train it to go to the left like this, just to go back, because then it's just going to swivel a lot. So you have to, and that's really the key to everything, that we need to be very, actually let's put it like this. And this is this slide. The data quality is really important because otherwise your output is poop. You know, you don't want that. Yeah. But this can be done in many different ways. So either how you collect, or how you pre-process, or how you augment it. So we did talk about something called overfit. And here's what that means. So let's say we have 7 data points, like here, and then we have a model that fits all these data points 100%, 0 error. But if we're using this to predict, based on if this is the x-axis and this is the y-axis, and we want to predict the y value based on x, right? If we go here, it's going to predict up here. And if we go here, it's going to predict here. It's not a very good prediction, right? Even if it's super exact in mirroring this data. And that is the danger when you use a very big neural network without enough data. Then you end up with this. What you want sometimes is a simpler model, right? So even though you have errors here, and here's quite a big one, and we'll call this an outlier, and we accept that, but anywhere where you go along on this x-axis, you have a pretty good estimate, pretty good prediction. And this is one of the really important tasks of a developer in this field, to make sure that you don't end up here. And it can be difficult to spot, and it can be difficult to know what tools to use, what techniques to use to get here. And sometimes, if you have enough data, you actually want to go and make it more complex. Right? Let's say the next level of simplicity here is just a straight line. But that wouldn't be any good, right? So this is just about right. Maybe a cubic function would be better, but where do we stop? Certainly before here, but after straight line. And that's the engineering part of it. So after doing that and after augmenting data, we're going to go into data augmentation in the next talk. And that's basically taking one photo and making more data out of it. One thing we can do is flip it to see. Here's using this data point with negative steering, going to the left. And we use the same one, we flip it horizontally and use it as a right driving example. It's important for our track because it's going around counterclockwise. So it has a bias towards turning left more than turning right. So we have quite a bit of time, so I'll just keep on going. And then yeah. No, I think we'll then we'll do the last part because we're, and then we'll take more questions. So we'll try again. With now I've added more training epochs, more steps back and forth. I've done more data augmentation and cleaned up the data, added noise to it, so made it darker in some parts, which helps when there's a shadow, and then we've seen darkened pictures. I've used special neural network techniques like dropout and poolings and stuff like that, which will come in the next section. So we'll try again. Let's see. TensorFlow. Here is a tool, a library written by Google, released I think as open source maybe 1.5 years ago, and all the code is written in Python. So it's and for those of you who are not developers here, that basically means that it's quite easy to get into. It's quite easy to try out at home. Just wait a little bit, develop more before you put it in a real car. But that's why it's fun to experiment with. So we'll try again with some more quality training.